Methodology. We have SwissProt sequence corpus of about 550K from the SwissProt. These sequences from SwissProt are given to the alphabet reduction technique, from which a corpus of reduced SwissProt sequences are generated. These reduced sequences are then given to the word2vec module, which then creates a high-dimensional vector representation of the entire SwissProt sequences. This forms the lookup table for the data that we would want to classify as AMP and non-AMPs. So this is part one of the process. In the second part, we have the actual antimicrobial peptides that we would like to classify. It's a data set consisting of AMPs and non-AMPs. These are gone through the same alphabet reduction technique that was done in part one, from which we obtained reduced AMP sequences for this data set. These sequences are then mapped to the lookup table that was generated earlier in order to get the high-dimensional vector representation of the antimicrobial peptides. Once we have these vector representations of the peptides, they are given to the classification algorithm, which learns to classify them as AMPs and non-AMPs. So one of the first steps in the whole process is to create embeddings. What we have are peptides. These are sequences which are composed of amino acids. To a machine, this is the same as a long word. Machine learning models take in only numerical input data. In order to give these sequences to a machine learning model, we need to first convert them to an appropriate numeric representation of the same length. In order to do so, we use word2vec and protvec. Word2vec was originally used in NLP, natural language processing, for learning word embeddings from raw text. This was to give meaning to the words based on their context. For example, if there were a document which had the words king, man, queen, and woman, it is likely that the embeddings which are created, the embedding for king would be closer to a man. It would also be closer to that of queen. And the embedding for women would be closer to queen and that of a man. Because these words tend to occur closer and more frequently near each other in the English language corpus. It is a computationally efficient predictive model. Words are transformed to a high-dimensional space. The way word2vec works is that it maps similar words nearby to each other. Now, in the sequence world, this is achieved by breaking down each peptide or sequence into a k-mer. So, for example, in the example sequence shown, if k-mer is 3, that is, we take 3 amino acids and group them. So, we have NGG as a k-mer over here. This is the word equivalent in NLP. Word2vec then maps these k-mers as vectors in the latent space, the size of which is defined by its vector size. So if this is 3-dimensional, so the vector size is just 3, but ideally the vector size would be 100, 200, 300, it could be anything. K-mers that occur close to each other would also be close in the latent space and have similar values. These values are the embeddings. If k-mer is 3, there will be 3 embeddings that are created whose summation creates the final embedding for the peptide. The closeness of each k-mer is defined by the context window. If the context window is 3, then it takes the current k-mer into consideration plus 3 k-mers looking ahead and looking behind in order to identify closeness. We use the skip-gram model for the same. Now, protvec is a continuous distributed representation of biological sequences. For each sequence, if k-mer is 3, the sequence is split into 3 mers, it is called, and for each time, 1 amino acid is foregone and we go to the next and again a 3-mer is formed. For k-mer equals 3, this will happen thrice. Embeddings are created for each of them and they are added up to give the final embedding. So for example, if the vector size is 5, then this is the kind of embedding we can expect. Now, one of the other techniques was reduced alphabet. The kind of properties for reduced alphabet we considered were conformation similarity, contact energy, hydropathy index, amino acid charges, and similarity matrix. There were various techniques in them. Groups were formed, and each group had a mapping to it. So if I explain with the help of an example, if the hydropathy-based grouping is used, there are 4 groups in it, and each group is mapped to a particular alphabet in this case. This alphabet has nothing to do with the actual amino acid which is there. It is just a representative mapping. So if we have an original sequence, first the reduced sequence is derived using this mapping that we have. And then based on this reduced sequence, the same techniques as described earlier in Word2Vec is implemented to create embedding of that sequence. Now, when there are multiple reduction techniques in play over here, because we created models without a reduction technique and with multiple reduction techniques. So if the reduction techniques into consideration over here are hydropathy and conformation similarity, we first generate embeddings for each of them. And then in order to combine the embeddings, we simply concatenate the embeddings obtained from both the reduction techniques. This forms the input to the machine learning model that we will be seeing.